Hi everybody, I hope this video finds you well. In today's video, we're going to be looking at one last probability-based topic called expected value. This is a little bit of sort of a tangent from the main part of our course, but it is a natural follow-up to discussing probability, which is what we've been doing for the last couple weeks. Expected value is sort of a way of doing some decision making with probability, which is a really important idea. So we're going to spend a little bit of time to talk about it. To do that, though, we're going to start with sort of a motivating example to sort of see the main idea behind this. Then we'll get into a definition and look at some examples. So, in this motivating example, let's suppose that you have a friend that offers to play a game with you. So, the game is pretty simple. You roll a six-sided die. If it comes up 1 through 4, you win, and your friend will give you $1. If the dice comes up as a 5 or a 6, however, you lose, and you have to give your friend $3. So the question here is this a good game to play? In other words, is this a good game for you to play in terms of making money, right? Because remember, when you get that 1 through 4, right, you're going to be earning $1, but there is a risk here when it comes up a 5 or a 6, you have to give your friend $3. So we want to sort of examine this. Now, from a probability standpoint, this is sort of very simple. There's only two things that can happen in this. You either win or you lose. So we can construct a model very easily here. So in terms of a probability model, remember that means we have to talk about the outcomes and their associated probabilities. Keep in mind here, there's only two outcomes. You either win or you lose. Now, we can think a little bit about sort of what those are worth to you, right? Winning, of course, means that you would gain $1 here, and losing, of course, would mean that you would lose $3. Now, what are the probabilities here? Well, you win when the dice comes up 1 through 4. Since there's 6 total things that can show up on the dice, and 1 through 4 will get you a win, that means that the probability of winning, of course, is 4 out of 6. We should be very comfortable with that since we've done a tremendous amount with probability. For losing, right, you lose at a 5 or a 6, so the chance that you lose is 2 out of 6. So, and of course, this is a probability model because 4 out of 6 plus 2 out of 6 is 6 out of 6, which is 1. We know that the probabilities always have to sum up to 1. Okay, so from a purely probability standpoint, this is a game where we know that your chance of winning is higher than your chance of losing, right? The probability that you win is 4 out of 6, but the probability you lose is only 2 out of 6. But the thing we have to be careful with here is we can't just simply look at the probabilities, right? Even though your probability of winning is higher, well, we know that winning is only $1, whereas losing is $3. So it can't just be based on the probabilities. So this is where we're going to use a new concept called expected value. We're going to combine these probabilities with their associated values and use that to determine if this is a good or bad game to play. So let's see how to do that. What we're going to do is we're going to calculate this thing called the expected value. And the way we do that is we take the value of the outcome, but we weight it with its probability. So we do that through multiplication. So we take the value of winning, which is that +1, and then we're going to multiply it with the probability that that happens, which is 4 out of 6. And then we're going to add that to this outcome. Well, this is -3 in terms of its value, but it happens 2 out of 6 times. So we're going to multiply that with 2 out of 6. What you're effectively doing here is you're averaging these outcomes according to these probabilities. So this should be pretty easy to calculate, right? If we just type it into a calculator, we can get that the expected value here is approximately, looks like we should get, if we multiply that stuff out, you should get that that's approximately about -0.33. So let's think about what this means here. Well, first thing that should jump out to us is that this is negative, meaning this negative component is larger than this positive component. That tells us that this is a bad game. In other words, even though our probability of winning is higher, the value of losing is so high that this is not a good game to play. So, since the expected value is negative or less than 0, this implies this is a bad game to play. In other words, what we're really saying is that while your probability of winning is higher than your probability of losing, that doesn't balance out the fact that when you win, you only win $1, whereas you lose $3. So overall, this is a bad game to play. Now, that we just did based on the fact that this came out as a negative. Let's see if we can say a little bit more about what this actual value means. Well, what it actually means here is we can say we expect to lose, well, this amount per play on average. So we expect to lose 33 cents per play on average. Now, this phrasing here is really, really important, right? The reason I want to call your guys' attention to this is if you think about it, it doesn't make sense if you just say we expect to lose 33 cents. Why doesn't that make any sense? Well, we know that when you play this game, only one of two things happens. You either walk away with an extra $1 or you walk away with $3 less. You either win $1 or you lose $3. So you never lose 33 cents. This 33 cents is only making sense as what we have to expect on average. So whenever you're talking about expected value, you're talking about what we expect to have happen on average. So the interpretation we would say here is that this is a bad game to play because we expect to lose about 33 cents per play on average. All right, so this is sort of giving you guys the idea of what we're going to be studying in this section, this idea of expected value. Expected value is about combining probabilities, something we're very comfortable with values. Now, for our class, these values here are pretty much always going to be just monetary values, but in general, they could be anything that we associate values with. But to make things easier, we're going to always have them be monetary amounts. Before we get to some more examples, let's go ahead and give a formal definition of expected value. So, expected value, here's our definition. The way you calculate an expected value is you take the sum of the probability of every outcome times the value of every outcome. So for every outcome in the probability experiment, you'll need to know its probability and you'll need to know how much it's worth to us. We multiply those things together and then we add them up. That's exactly what we did in the last one where there were only two outcomes. You'll notice though that in this definition, this would apply to any sort of situation, one that might have more than two outcomes. You just add up the probabilities times their values. How do you interpret expected value, or what does it really mean? Well, expected value tells us how much we expect to win or lose per play of the game on average. And again, that mention of on average is so important because that expected value isn't going to be what happens on a single play of the game. It's what we expect to happen on average as we play this game many, many times. How do you use expected value to make a decision? Well, if the expected value is greater than 0, meaning if the expected value is positive, then the game that you're looking at is good to play. If the expected value is negative, then the game is bad to play. And if the expected value is exactly 0, then we would say that the game is fair to play. Now, I want to make a couple quick mentions about this. First, in terms of good and bad, you have to realize that good and bad are going to be perspective driven. Let's take a moment and look back at the first example. In the first example, we calculated the expected value as negative 0.33 and used that to conclude that the game was bad to play. That's from our perspective, right? That's from our perspective that this is a bad game to play. Since this is a bad game to play from our perspective, it must be a good game to play from our friend's perspective. If we redid this, where this was losing, and it was -1, and it was 4 out of 6, and this was winning, and it was +3, and it was 2 out of 6, that would be from our friend's perspective. This would come out as positive 0.33, and it would be a good game to play. Because if we're losing the game, our friend must be winning the game. So that's what we're sort of making sure that you guys understand, that this is a perspective-driven thing. Something that's good from one person's perspective is going to be bad from the other person's perspective. Second thing I want to mention here is what exactly does it mean to be fair? Fair here does not mean that the chance of winning is the same as the chance of losing. It means that the value from winning equates to the value from losing. In other words, the game is fair, in other words, says that if you played this game many, many times, neither person would win or lose more money. In other words, even though one person might have a higher chance of winning, their value would be lower and it would equate out to a fair game. So fair doesn't mean that each person has the same chance of winning. It means that the value overall is equal for both sides. That's what we're saying when we say the expected value is 0. Okay, so now that we have this definition, this formal definition of expected value and this way of interpreting it, let's look at one more example of actually putting this to use here. Okay, so let's take maybe our friend comes up with a different sort of game that they want to play, and they offer this game. So our friend offers to play this game with us. We draw a single card from a standard deck of cards. They say that if the card we draw out is an ace, our friend is going to give us $5. If the card is a face card, then the friend is going to give us $3. Remember, face card just means jack, queen, or king. Otherwise, if it comes out anything else, so basically any number card, we have to give our friend $2. So in other words, we have two ways of winning. If we get an ace, we get $5. If we get a face card, we get $3. Otherwise, we're going to lose and have to give up $2. So we want to do a couple things with this. First, we're going to just answer some basic probability questions just to make sure we're still comfortable with that. So we're going to build a probability model for this game and then calculate a couple probabilities. And then we're going to use this interpret this expected value to decide if this is a good or bad game to play. All right, so let's go ahead and build our model first. Okay, so let's think about the outcomes and their probabilities. So what are the outcomes here? Well, according to this, the outcomes are if we get a ace, that from our perspective is a +5. We win $5. A face card, that's a +3 from our perspective. And otherwise, which is a -2 from our perspective. A -2 to match the fact that we have to give our friend $2. So what are these probabilities? Well, for an ace, we know that that probability would be that there are 4 aces out of 52 cards. For face cards, we know that there are 4 jacks, 4 queens, and 4 kings. So that's going to be 12 out of 52. For this guy, it's everything else that remains. But we can do that sort of easily by just doing 1 minus the stuff that's up here, right? Because all the other cards that remain are going to cause us to lose. So we can do that. And if we calculate that, that would be 52. If we make common denominators here, 52 minus 4 minus 12. And it looks like that should come out as 36 out of 52. And if we add those up, that's 4, 16, 36 makes 52. So that really is a probability model. So we got a 4 out of 52 chance that we win $5, a 12 out of 52 chance that we win $3, and a 36 out of 52 chance that we lose $2. All right, now let's answer some probability questions. Next question we want to answer here is, what is the probability that you win money on one play of the game? So probability, win money on one play. So if you're going to sit down and play this game only once, what's the chance that you win money? Well, there's 2 different ways that you can win money here. You can get the ace or you can get the face card. So we just add those probabilities because it doesn't matter which one, both will win us money. And we can see that the probability that you win money on one play is 16 out of 52. If we wanted to actually understand how likely that is, we can actually do that division. And we can see that that comes in at about 0.308. So in other words, there's about a 30.8 or about 31% chance that if we play this game once, we will win money. Not saying how much money, could be $5, could be $3, but about a 31% chance that we win money. Okay, let's calculate another probability. Let's calculate the probability that you win money on 4 plays in a row. So now we want to do win money on 4 plays in a row. Okay. How would we do that? Well, to win money on 4 plays in a row, this has to happen 4 times in a row. Now, we know that when you have to have multiple events happen, you have to use the multiplication rule. So we're going to multiply this with itself 4 times. Remember, when multiplying something with itself, that's the same as raising it to a power. So this would be 0.308 to the 4th. And if we actually do that, we would see that that would come out as about 0.009. So there's just under a 1% chance that if we played this game 4 times in a row, we would win all 4 times. Okay, so all of these things are just probabilities, right? This is just our probability model. This is just talking about probabilities of winning money. Now it's actually time to make use of the idea of how much money we're winning. That $5, that $3, and the fact that we're risking $2. So now we're going to go ahead and calculate this expected value. So let's go ahead and do that. So how do we get this expected value? Well, what we're going to do is we're going to take the value of each outcome, multiply it with its probability, and then add those up. So the first outcome is that we win $5. So we'll do positive 5 times its probability, which is 4 out of 52. Then we're going to add that to the next outcome, which is positive 3 times its probability, which is 12 out of 52. And then we're going to add that to the last one, which is an outcome of negative 2, and its probability, which is 36 out of 52. Okay. So, sorry about that. That's a little squeezed in. So let's go ahead and just rewrite that real quick to make it a little bit clearer looking. So we'll just slide this guy over. The expected value here, like we said, is positive 5, 4 out of 52, plus positive 3 times 12 out of 52, plus negative 2 times 36 out of 52. So each of these is the value of the outcome times the probability of the outcome. Now we can just type that into our calculator and see what sort of expected value we're going to get. So 5 times 4 divided by 52, and then plus 3 times 12 divided by 52, and then plus negative 2 times 36 divided by 52. Looks like that should come out is about negative 3.08. So there is our expected value here. So this expected value, right, is a negative. So that immediately tells us, right, that since this expected value is less than 0, this is a bad game to play. In other words, what this negative expected value is telling us is that even though we win $5 or $3, which is more than losing 2, those are not high enough payouts to make up for the fact that we often lose. So these are not quite high enough to compensate for the fact that the chance of winning is pretty low and the chance of losing is pretty high. How bad is this actual game? Well, we can go ahead and actually calculate that. So we can say we expect to lose 30.8 cents per play on average. So we're saying that this expected value tells us how much we expect to lose per play on average. So every time we sit down to play this game, we're expecting to lose about 30.8 or about 31 cents per play on average. Now, this this is mathematically the correct way to interpret it, but let's make it a little bit easier on ourselves and sort of give ourselves a context of understanding this on average. So let's imagine you're going to sit down and waste a tremendous amount of time playing this game with your friend. We're going to say, let's interpret this if you played this game 200 times. So now we're going to say what happens, or what do we expect to happen after 200 times? Well, if you think about this, this expected value is what we expect to happen per play. And we're going to play 200 times. So we can calculate. We're expecting negative 0.308 per play times 200 plays. And if we do that, negative 0.308 times 200 would be negative 61.6. So we expect to be down around $61.60 after 200 plays. So this hopefully right here helps you guys really understand what we mean by expected value. If you sat down and you played this game 200 times, well, you do not expect to lose all 200 times. If you lost all 200 times, you would be down $400. If you got face cards all 200 times, you would be up $600. If you somehow got aces every time, you would be up $1,000 because 200 times 5 is 1,000. But we don't expect any of those things to happen. Instead, we expect you to get some aces, some face cards, and a lot of other stuff. After you winning and your friend winning and back and forth, we expect that after 200 plays, you would be down about $61.60. And the idea here is that since the expected value is negative, the more and more you play, the worse and worse things are for you. Because overall, the game is weighted against you. So the more and more you play, the lower and lower this is expected to be, because overall, the game is a bad structure. Does this mean that if you sat down and you played once that you're going to lose? Not necessarily, right? We said that if your chance you win is about 30%, 31%. But we're saying that the longer you play, the more you play, the worse and worse it is for you. Because overall, the game is a bad game. In our next video, we'll go through a couple more computational examples, seeing how to work through and build probability models. That'll be sort of review, and then continue to examine this expected value.